All right, thank you for joining us today for our Air Quality and Healthy Hearts webinar. And apologize for starting a few minutes late. We wanted to make sure we got as many people on the line as possible before we got started. So I'm just gonna say a few things before I introduce the speaker and we actually get started on the presentations today. So if you haven't noticed already, on your navigation bar on the right side of your screen, there is a handouts drop down. If you look there, there is a copy of the slides if you haven't received those already. So feel free to download those and keep those and share them with anyone you think might be interested in this information. At any point, we are going to have a 30-minute Q&A session at the end, at the top of the hour. So it's from 3 to 3:30. We will have a Q&A session. And so we'll answer as many questions as possible during the webinar. And let me make sure. And sorry, it doesn't say that on the, oh, it does say that on the screen. Okay, I wanted to make sure everyone was aware that we actually went till 3:30. Now, if you have to leave at 3 and you have a question that you've submitted and you would like some feedback on a question, we can and we will follow up on questions. We'll receive those, and you also have contact information on the slides if you'd like to follow up with one of the presenters today. So at any point during the webinar, please feel free to type in a question, and we will hold all of those to the end of the screen, or the end of the presentations. Your microphone has been muted for the webinar. Okay, next slide, please. We are offering certificates of attendance for watching the live webinar today. You need to be logged in, registered, logged in, and attend for about 60 minutes to receive the certificate. If you have people in the room with you who would also like a certificate, you can just type names in the questions box and we will make sure they get certificates as well. If you are not logged in and you're on the phone line only, you can send names to this email address and we'll make sure you also get certificates. And those will be sent out via email within a week of the webinar. This webinar, I forgot to mention, is also being recorded for future viewing. You can't receive a certificate for that, but you will be able to watch it later, and it will be posted to the website. The link is on the title slide, and that is where the recording will be posted. Next slide. So this is just actually, you can move to the next slide as well, slide 4. Slide 3 is a summary of the webinar just for your records, so you have a complete document for your records. And so the first presenter I'd like to introduce is Dr. Wayne Cascio. Dr. Cascio is a board-certified cardiologist, and he is the director of the Center for Public Health and Environmental Assessment with EPA's Office of Research and Development. And with that, I'm going to turn it over to Wayne so he can start the presentation.
Thank you, Michelle. And
sure.
Can you hear me?
Yep, you sound great, Wayne. You can go ahead.
Can we advance to the first slide? And so hello, everyone, and I'm really pleased to be here today to add my welcome to the Air Quality and Healthy Hearts webinar and to set the stage for Drs. Rophold and Ward-Cavanis. I will be talking about EPA's mandate and the mission related to air pollution and why our team in the Office of Research and Development conducts cutting-edge research and to investigate public health and air pollution's effects. Next slide. The overarching mission of EPA is to protect human health and the environment. The Office of Research and Development, or ORD, contributes to EPA's mission by providing the scientific foundation for the agency to execute this mandate. ORD provides research on statutory requirements and specific environmental challenges. ORD scientific experts provide research in support of US EPA's program and regional offices. When local, state, national, and tribal officials come to us for technical support, we also help them respond to their contemporary environmental challenges. ORD looks to the future needs of our country as well by conducting innovative and anticipatory research applied to a broad range of US EPA program and regional needs to solve longer-term environmental challenges and provide the basis for future environmental protection. Next slide. ORD has 6 national research programs that set the research plans. The research described today is supported by the Air and Energy National Research Program under the direction of Dr. Brian Hubble. The Air and Energy Program portfolio includes research to better understand air pollution, air quality monitoring, and decision support tools to protect public health and the environment. The other research programs include the Sustainable and Healthy Communities Program, Safe and Sustainable Water Resources, Chemical Safety for Sustainability, Health and Environmental Risk Assessment, and the Homeland Security Program. Next slide. Nearly 50 environmental laws authorize the US EPA's national research programs. There are several which you may be familiar with, like those listed here. For today's webinar, we'll focus on the Clean Air Act. The Clean Air Act is the comprehensive federal law that regulates air emissions from stationary and mobile sources. The Clean Air Act states that EPA shall establish a national research and development program for the prevention and control of air pollution. Next slide. The Clean Air Act requires the EPA to set national ambient air quality standards for 6 common air pollutants that include particulate matter, ozone, nitrogen dioxide, sulfur dioxide, carbon monoxide, and lead. These are also known as the criteria air pollutants. These pollutants are found all over the US. They can harm health and the environment and cause property damage. Primary or health-based standards are those that, in the judgment of the administrator, are requisite to protect public health with an adequate margin of safety. The secondary or welfare-based standards are those that specify a level of air quality, the attainment and maintenance of which, in the judgment of the administrator, are requisite to protect the public welfare from any known or anticipated adverse effects. Welfare effects include impacts on soils and water, crops, vegetation, man-made materials, animals, wildfire, weather, visibility, and climate. Next slide. EPA's Office of Air and Radiation evaluated the costs and benefits of the Clean Air Act and published the second prospective study, which looked at the results of the Clean Air Act from 1990 to 2020. A few key findings are illustrated here on the slide. This chart on the left shows the health benefits of the Clean Air Act programs that reduce levels of fine particle and ozone. Note that in 2020, the Clean Air Act amendments are estimated to prevent over 230,000 early deaths. On the right, the circle graph shows that the benefits of the Clean Air Act compared to the costs are estimated to be 30 to 1. While there are benefits from reducing ozone exposure, visibility impairment, and ecological impacts, most of the benefits, as much as 85%, are attributable to reductions in premature mortality associated with the reductions in ambient PM. The huge benefit we observe and the measure from reducing PM is one of the greatest reasons ORD has focused on the health effects of particulate matter. Next slide. Anna and Caven have outstanding presentations and will go into greater detail about particulate matter and its health impacts. To get us started, let's define what particulate matter is and generally what its public health and environmental impacts are. Particulate matter is an aerosol mixture of very small solid and liquid droplets. They can be formed as primary particles emitted directly from both man-made and natural sources like smokestacks, vehicles, construction sites, or wind-blown dust, wildfires, and volcanoes. Secondary particles are produced through complex atmospheric reactions of chemicals. Particulate matter is classified by the aerodynamic diameter of the particle. For example, coarse particles, which are known by PM10, have an aerodynamic diameter between 2.5 microns and 10. And as shown in the image, about 5 to 6 such particles would be as wide as a human hair. Fine particles, or PM2.5, have an aerodynamic diameter of less than 2.5 microns. And ultrafine particles, even smaller than that, at less than 0.1 micron. Related to human health, particulate matter is of concern because it's associated with serious health effects such as worsening of ischemic heart disease and heart failure, heart attacks, disturbances of heart rhythm, aggravation of asthma, decreased lung function, and premature death. Several decades of research have shown that both short and long-term exposure to air particle pollution produces cardiac health effects. Next slide. Well, with that said, it's an honor to introduce our speakers, Dr. Anna Ruppold and Dr. Caven Ward-Cavanis, who are going to tell the story of some new findings from 4 papers. Dr. Ruppold is a statistician with the Center for Public Health and Environmental Assessment in EPA's Office of Research and Development. She is leading a project aimed to integrate public health messaging with environmental models and understanding their effectiveness in reducing the burden of environmental impacts on public health. Anna has conducted clinical and epidemiologic research studies of health effects from air pollution and has authored many studies now specific to wildfire smoke impacts on health. Next slide. Before turning the webinar over to Anna, I'd like to introduce Dr. Ward-Cavanis. Caven is a computational biologist with the Center for Public Health and Environmental Assessment in EPA's ORD. He's the principal investigator of EPA Cares, a resource of electronic health records and environmental data that assists researchers with environmental risk studies in vulnerable patient populations using novel approaches. Caven also leads investigators that use molecular data to identify susceptible populations and early indicators of health risks from chemical exposures in the built environment. So without further delay, Anna, are you ready?
Yes, Wayne, thank you very much. Can you hear me well?
We can.
Okay, thank you. Next slide, please. So I'm going to talk about a couple of studies a couple of recent studies that we have done on tracking the trends in air quality and changes in cardiovascular mortality, and a couple of studies, and referred to the results from a couple of studies from wildfire smoke exposure. I would like to acknowledge that this work is a product of collaborations here at EPA, as well as with colleagues at California Department of Public Health, University of San Francisco, and CARES program. This is a different CARES program than the one Caven leads at EPA. Next slide, please. The air quality has been improving in most parts of the country due to, in no small part, an enactment of Clean Air Act and its amendments, as Wayne mentioned, and also due to various technological advances. This figure illustrates temporal trends in concentrations of pollutants regulated by national ambient air quality standards. The vertical axis gives us a % change above, if it's above the gray line, positive, or below, if negative, from the current standards. So you can notice a significant improvement, downward trend can be observed, particularly for sulfur dioxide, fine particulate matter, coarse particulate matter, and steady declines in ozone, NO2, and other pollutants. So the question I want to start today with is, and the question that motivated our research, is whether these improvements in air quality have resulted in measurable improvements in health, and what source sectors contributed the largest change. This is a fair question. When sources of air pollution are intervened upon, either by regulations or technical advances, the cost is economic, and some sectors may experience a higher cost than others. The economic burden is not trivial, and actions should be taken to evaluate whether the expected health benefit has been achieved and is consistent with the risk assessment projections. Next slide, please. Reductions in fine particulate matter related air pollution occur mainly through reductions in emissions at the source, which does not necessarily result in equivalent reductions in human exposure. This graphic describes main source sectors that contribute emissions and processes that guide the conversion of the emissions to exposures and concentrations of air pollutants. There are 5 major sectors, and they include road and non-road mobile sources, area sources, large point and other point sources. These sectors each are composed of further individual sources, and many of them are results of human activities, but others are the results of natural activities such as wildfires. The primary emissions include nitrogen dioxide, nitric oxide, sulfur dioxide, ammonia, volatile organic compounds, elemental and organic compounds. In the atmosphere, these emissions are converted to concentrations of primary air pollutants, particulates that include sulfates, nitrates, and elemental and organic particles. We use CMAQ modeling framework. CMAQ stands for Community Multiscale Air Quality Model to represent conversion of emissions to estimate exposures at the population level. CMAQ is a first principles model of physical and chemical processes in the atmosphere, and it simulates distribution of variety of airborne pollutants continuous in time on a complete spatial grid. As such, that model allows us to estimate exposures at any location in time and space, and can account for the impact of emissions released at the source away from the location where we're interested in estimating the exposure. In the case of wildfires, for example, emissions are released at the source, but populations are exposed to concentrations at great distances from the source. Finally, to keep in mind, the exposure is measured in terms of concentrations, micrograms per cubic meter, while emissions are measured in terms of mass, metric tons per year. So CMAQ is not the only way to characterize exposures. Concentrations are also measured at the monitoring sites, and one can access the data at EPA website, However, monitors are not positioned everywhere at all locations and do not collect data continuously. Next slide, please. These figures illustrate how CMAQ prediction grid looks like, and this is an image of annual PM2.5 concentration in 1990 and in 2010. It's easy to observe the decline in concentrations around the country. That decline has been steady throughout the period, but depended on locations. Locations that had initially the highest concentrations also tend to have the largest decline on average. So you can see in the industrial Midwest, where at the beginning of the time period, the concentrations were the highest. Toward 2010, they are reduced most significantly. Next slide, please. In fact, according to CMAQ estimates, the PM2.5 concentrations between those 2 years declined by 30%. And if we look at by components, PM2.5 main components, nitrates, sulfides, elemental carbon, and organic carbon mass. Nitrates decreased by 23%, sulfates decreased by the largest amount of 42%. But during that same period, cardiovascular mortality rate has been reduced by 46%, even larger percentage. And most of that reduction is because of the change in care and lifestyle. However, approximately 10 to 15% is estimated of reduction of CV mortality has not been explained. So in this work, we investigated whether the portion of the observed trend in cardiovascular mortality is associated with the changes in long-term concentrations, annual ambient concentrations for PM2.5 and its main constituents. And then the second research question was of interest to us was to relate that change to the changes in emissions and characterize the change in cardiovascular mortality related to PM2.5 by each of the emissions factor. Next slide, please. Cardiovascular outcomes are primary outcomes when considering fine particulate matter exposure due to the causal link with a number of clinical outcomes. Briefly here, 3 main pathways have been identified in the literature by which clinical outcomes occur, and that is through activation of autonomic system, systematic inflammation, and direct bloodstream effect. These mechanisms can lead to have been reported to lead to outcomes such as heart failure, cardiac arrest, stroke, pulmonary embolism, and other type of outcomes. Next slide, please. So the goal of our analysis, to recap, was to estimate the portion of the observed trend in cardiovascular mortality associated with the changes in ambient PM2.5 concentrations. And this slide takes us, it illustrates the process by which we did that. First was to quantify PM-related change in mortality. This quantity is measured in number of cardiovascular deaths per 100,000 people and combines 2 elements: mortality per unit change of PM2.5 or its components, as well as the total change in the concentration of PM2.5 and its components. We do the same calculation then for each component separately, controlling for the other copollutants. And then the end product of the first step is to have a number of deaths per 100,000 people related to the change in PM2.5. That as that can now be linked to the changes in emissions at the national level, and we focused on 4 well-defined pathways of precursor emissions to PM2.5 formations, and that is nitrogen oxides emissions to nitrate, SO2 emissions to sulfate PM2.5 concentrations, and primary EC emissions to EC fine particulate matter, and similarly for organic carbon. In the last step, now because we know the distribution of each emission with respect to the sources, we can now characterize the change in cardiovascular mortality attributed to the total change in emissions from each of the sectors. Next slide, please. We estimated that PM2.5 related reduction was associated with 10.4 deaths per 100,000 reduction in cardiovascular mortality, which is approximately 5.7% of the total of 190 deaths reduction from all causes. So in other words, 5.7% of the trend in cardiovascular mortality is attributed to the changes in PM2.5 concentrations. In the next slide, that result is given broken down by the source categories, where each row distributes PM-related mortality by emission to PM relationship. So conversion of sulfur dioxide to sulfate resulted in 11.1 deaths per 100,000. So each number represents number of deaths per 100,000 over the 20-year period. Nitrogen oxides to nitrate conversion accounted for 8.1 deaths per 100,000. The largest contributors from sulfates were large point and other point sources. Nitrogen oxides, the largest point sources were mobile and large point sources. Similarly for elemental carbon, the largest source was the largest contributor to the reduction in mortality were mobile vehicle sources. We also saw some deficit or increase in mortality related to these emissions, and they tended to be associated with area sources, which were highly coincidental with areas of large wildfire impacts. In the follow-up study, next slide, please. In the follow-up study, we examined how PM-related change in mortality varied with respect to socioeconomic composition of the community. In this graph, each dot represents a county. There's over 2,000 in total. And deprivation, to represent deprivation, we used census variables related to poverty, income, education, unemployment, type of housing, and so forth. So counties with the lowest index of deprivation, the ones in purple, had the highest and largest overall change in PM2.5, highest initial levels of PM2.5 and the largest overall change in PM2.5. While the counties with the highest index of deprivation, those on the right-hand side in orange, you can notice that on average, at the beginning of the time period, they had the lowest level of PM2.5, and less reduction in PM2.5 overall. But that rate of reduction actually increased in the later time period. In the next slide, the mortality, this is cardiovascular mortality, also decreased the decrease in mortality also varied with respect to the deprivation index. Where the highest mortality rates were seen in the communities with the highest deprivation, and they had the largest change in cardiovascular mortality overall. When we break, next slide, please. When we break this down, the overall 5.7% of annual decrease in cardiovascular mortality that is attributed to change in PM2.5 concentrations was varied by deprivation index of the counties, and the counties with moderate deprivation index had the greatest PM-related change in mortality. Counties with the highest deprivation had a smaller change in PM mortality due to smaller declines in PM2.5. And the gap attributed, the gap between those at the highest level of deprivation and the lowest level of deprivation changed over time, and it reduced over time because of two factors. One, that PM2.5 in the communities with the highest deprivation actually started to decrease faster, and there was a greater benefit per microgram of cubic meter change in PM2.5. So overall, these results suggest progress is made on average, but there's also individual communities that there's still concerns, but we also have new emerging issues such as wildfires. In the next slide, please. In the next slide, this is a slide borrowed from a colleague in California, Jason Vargo, who evaluated the number of person days exposed to heavy wildfire smoke plumes. And you can see over the years, the number of people and the percentage of people in California has increased that are exposed to smoke from wildfires has increased rapidly. There's wildfire smoke contributes significant economic and public health burden. One estimates between $11 and $20 billion annually. Again, most of that is due to the estimates of mortality. The next slide, please. So together with the colleagues at California Department of Public Health and University of San Francisco Medical Center, we a few years ago we studied emergency department visits related to cardiovascular and cerebrovascular outcomes during the wildfire smoke season in 2015. At the time, that was the largest smoke season, but has since been, I think, overpassed each year. We noted a strong association between a number of cardiovascular outcomes, specific outcomes, as well as overall grouped together, and cerebrovascular outcomes. The impacts were greatest among individuals 65 years and older. They were the order of magnitude for risk for those individuals was on the order of the magnitude as respiratory outcomes. The impacts and the impacts were strongest on the heavy, proportional to the smoke density in terms of PM2.5. So here, smoke density was characterized in terms of PM2.5 concentration as light, medium, and dense. And in a follow-up study, we examined, in the next slide, please. We also had an opportunity to look at the endpoint that is not captured in the literature that is not captured in hospital admissions or ED emergency department database, and that is out of hospital cardiac arrest from CARE's cardiac arrest registry to enhance survival. That is a registry put together to improve, to study and improve survival rates among cardiac arrest. This is an important endpoint because it's not uncommon, and it has a very high fatality rate of 90%. So only 30% of the individuals actually make it to the hospital. And those are the individuals that we studied. So in the next slide, just want to show some results of this study. Again, the smoke here is represented as light, medium, and heavy. But just to play with your eyes, they're reversed. Now they're heavy, medium, and light. And you notice that odds ratios increase on heavy smoke days significantly, but I think the estimate is 70% with large confidence intervals because it's still a rare event. And no significant change was noticed on medium and light smoke days. However, when we stratified those outcomes based on the indicators of socioeconomic status, then some stratification of the risk for medium and light smoke days is noticed. It's not significant. The difference is not significant, but among the higher socioeconomic status communities, we seem to have a protective effect, probably reflecting behavioral change and adoption of exposure-reducing measures as opposed to lower socioeconomic indicators. That's certainly something that we're going to work forward to in future years to communicate these results and share them with the wider community. And that is my last slide, so I'm going to turn it over to Kevin.
Right, thank you very much, Anna. Can everybody hear me clearly?
Yes.
Yep, excellent. All right, well, I must say thank you to both Anna Rappold and Mike Cassio for the excellent introduction, and also leading us into this sort of final presentation, where I will talk about our efforts at the Environmental Protection Agency to really do research on the most vulnerable people within the population and how we're able to bring in novel electronic health record resources in order to allow us to do that in ways that we were unable to in previous research studies. Next slide, please. So on this next slide, I'm simply showing an excerpt from the research study that was recently published that captures most of the work that you'll see here, which was published in the Journal of the American Heart Association, been really the entire focus of this initial research project that's really been the spearhead of a much wider effort to study air pollution exposures in vulnerable patient populations, really focused on mortality, which is going to be the focus of the rest of my talk. Next slide, please. So this will be a bit of a refresher, harkening back to an image that you may recall earlier from Dr. Wayne Cassio's slides, really highlighting the importance of studying PM2.5, which is particulate matter less than 2.5 micrometers in diameter, as a public health emergency that's really been ongoing for many years. And as Anna showed with the wildfires, is still very much present. So air pollution in general is responsible for about 3.3 million premature deaths worldwide, with the vast majority of those coming from the particulate matter, particularly that fine particulate matter that's been highlighted over the course of these presentations you heard thus far. And then on the right side of the slide, you can see what we might refer to as a pyramid of effects from air pollution, where at the top of the pyramid, you see the sort of the most severe effects of air pollution being death, which is responsible for about 90% of the monetized benefits that we saw in the Clean Air Act, where we saw such outsized benefits as relative to the costs that have been associated with that over the years. And then as you step down the pyramid, level by level, you get to less and less severe health effects, but which are nevertheless present in wider and wider subsets of the population for it. And then obviously the proportion of the population that is susceptible to these effects also increases as you go down. And so in the way that you might summarize this all together is that for the generally healthy population, most of them are only susceptible to mild effects of air pollution, such as mild respiratory systems, lung function decrements, or mild levels of inflammation. However, there are a group of individuals that are both highly susceptible to air pollution and may experience things such as emergency room visits, hospital admissions, or death. However, this is a relatively small proportion of the population, and they are typically characterized by having some pre-existing condition, which has sort of motivated a lot of my studies. Next slide, please. So one of the most severe pre-existing conditions that can exist is heart failure, which sort of motivated our initial study to look at heart failure, PM 2.5 exposure, as well as cardiovascular mortality and morbidity via collaboration with the Carolina Data Warehouse for Health, which is organized at the University of North Carolina. So through this collaboration, which is a very unique one, and we are very thankful to our collaborators for allowing us to work with them and be able to pull this resource together. We were able to obtain health record data on about 40,000 individuals who were diagnosed with heart failure over a 12-year period from 2004 through 2016. Along with obtaining the diagnoses of these individuals, we obtained their residential address history, vital status, and disease diagnosis history, really allow us to do a complete analysis of this group of individuals, not just for mortality, which we'll see here, but for a number of other health outcomes, even expanding into clinical labs and vital status such as blood pressure and heart rate. Now, on their own, the electronic health records represent a major resource which has been used for a number of health studies over the years, particularly as they've grown in popularity and utilization over the past decade or so. Our unique aspect to this was to bring this together with environmental exposure data that we have both at the EPA as well as through several other academic collaborations. So we paired this both with PM 2.5 data from our EPA regulatory ground-based monitoring network, as well as from a machine learning model, which is able to predict PM 2.5 exposure across the entire continental United States at a very fine spatial resolution. So at a 1 by 1 kilometer resolution, they're on a daily level. So an enormous amount of data that we're able to link to our nearly 40,000 individuals and all of their health information over about a 12-year period. Next slide, please. So stepping back, so I've mentioned that heart failure is one of the most severe forms of cardiovascular disease, and these individuals really represent some of the most vulnerable patient populations that we could examine. This slide really, I think, brings that home for us and sort of magnifies the clinical problem that is heart failure. So it affects nearly 6 million individuals. That's expected to grow to 8 million individuals by the year 2030. So it's increasing in prevalence, which is uncommon for a number of cardiovascular diseases. It's about 500,000 new cases per year, and the most common diagnosis in individuals age 65 or older, and the most common cause of death with about 1 out of every 8 deaths for it. We chose mortality for the study because mortality is perhaps the most severely affected condition, if you will like to call it that, affected by these heart failure individuals, and that the 5-year mortality rate is about 50% for these individuals. So anything that we can do to understand mortality risks in the population represents a substantial potential benefit to them in terms of what we can do to extend that lifespan and to increase or decrease that more extremely high mortality rate. And then the costs are extremely large at $30 billion annually, and like the prevalence is expected to increase sharply to almost $70 billion by the year 2030. Next slide, please. So here on this next slide, we get into a bit more about the population cohort itself. So as I said, we had about 40,000 participants, so it's represented by about 1.6 million hospital visits. All of our data came from the University of North Carolina Healthcare System, which is a system of hospitals and clinics distributed across the state of North Carolina. You see there in the light blue dots all of the main University of North Carolina hospitals. We chose not to show all of the clinics simply to keep the map a little bit simpler. The blue star in the middle there represents the main University of North Carolina hospital system located on the UNC Chapel Hill's flagship campus there. And then the yellow triangles are our PM 2.5 monitoring network. And you see we have very good co-location between the monitoring network as well as our hospital systems. That occurring because generally both hospitals and EPA regulatory monitors are placed near where population centers are. And so we get a nice overlap between what we're using to assess PM 2.5 and where most of our patients occur. Next slide, please. As Anna nicely showed, concentrations of PM 2.5 have been declining over the years. North Carolina has experienced a quite substantial decline in PM 2.5 concentrations over our study time period. The top representation of our state there with all of the red and the yellows represents the PM 2.5 concentrations in 2004, where the maximum concentrations seen were up to 14 to 16 micrograms per cubic meter of annual average PM 2.5. Now here in the green on the bottom there, you see concentrations in 2016, where we actually did not, within our study at least, observe any concentrations that were above the National Ambient Air Quality Standard for PM 2.5 on an annual average basis of 12 micrograms per cubic meter. So in summary, this means we have quite good air quality within the state of North Carolina, but this also presents a unique area where we can study effects that are right around the regulatory border of 12 micrograms per cubic meter, because we have individuals both above and below that level, allowing us to see what the effects are near that border, which is of great public health interest and wider interest to the scientific community. Next slide, please. So this slide just details our modeling approach here. So we're really trying to estimate the risk of mortality per 1 microgram per cubic meter increase in long-term PM 2.5 exposure. And that 1 microgram per cubic meter increase is going to be an important quantity to remember, which I'll discuss more on the next slide. We adjusted for the age at heart failure diagnosis, race, sex, and neighborhood socio-demographic conditions. If you recall from some of the slides that Anna just showed, there are differences between PM 2.5 exposure by area indexes of deprivation. And so we wanted to control for that to be more confident that what we are looking at was an effect of the particulate matter and not just socio-demographic differences, which we know can very much impact mortality as well. We chose to stratify our models on the age at diagnosis, race, sex, pre-existing conditions, as well as the type of heart failure. And this is really the first time that we've been able to look at clinical subtypes of heart failure and what their environmental health risks may be, and if they differ by subtypes of heart failure, which are typically grouped together and analyzed all as one. And our final population size is about 23,000 individuals, of which we observed almost 4,500 deaths over our study time period. Next slide, please. So this next slide really captures the primary results of our analysis. The two upper and lower graphs are identical with respect to their layout. On the y-axis, you have the increased risk of mortality as represented by the hazard ratio. for those of you who might be familiar with that statistical quantity. And on the x-axis, you have the various populations that we looked at, starting with our overall population, then moving to stratifications on age at diagnosis, sex, race, and then pre-existing conditions there at the very end, from type 2 diabetes, ischemic heart disease, peripheral arterial disease, chronic obstructive pulmonary disorder, hyperlipidemia, and then finally hypertension at the end. The top graph represents the entire cohort, and then the bottom graph represents just those individuals that are below the 12 microgram per cubic meter standard that we have here. And the takeaway is that across all stratifications that we looked at, no matter what their age at diagnosis was, their sex, their race, or any pre-existing conditions, we observed very strong associations between annual average PM 2.5 and mortality in this population, as we might expect. Now, I mentioned previously that 1 microgram per cubic meter differential with respect to which we are analyzing the increased risk of mortality was going to be important. And that's important because the effects that we're seeing here on the slide are typically the types of associations that we would see per 10 micrograms per cubic meters in the general population. So we're noticing effects here that are much, much stronger than what's been reported across the literature within the general population, and really fits into a broader thematic that people with pre-existing disease, in particular pre-existing cardiovascular disease, seem to be at much stronger risks from, or seem to have much more elevated environmental health risks as compared to the general population. The other takeaway from this slide is that for the heart failure community, they seem to be at such an elevated risk that other pre-existing conditions such as type 2 diabetes, ischemic heart disease, or even hypertension don't do much to modify that risk. Now, whether this represents an absolute thresholding effect, or if there are conditions which might even elevate their risk much further, still remains to be seen. But at the very least, we do feel confident that we are really looking at the upper levels of that pyramid that I showed before, where mortality risks are much more elevated relative to the general population, and may not be modified by a lot of other pre-existing conditions. Next slide, please. Now, this next slide digs a little bit deeper, looking at some sensitivity analyses, just so we can be more confident that our results are stable, and then breaks it down by diastolic versus systolic heart failure. So if you see on the rows represent each level of analysis, starting with our primary analysis, which you saw on the previous slide, and then the individuals restricted to exposures less than 12 micrograms per cubic meter, which you also saw on the previous slide on that bottom graphic. Then we also restricted individuals who were less than 30 kilometers from a monitor, and still saw very strong association. So that sort of gets at the idea that we might have some exposure misclassification with individuals who reside further and further from one of our monitoring stations, but that does not seem to be impacting our results to any large degree. And then finally, we adjusted for county-specific mortality rates, recognizing that within even a relatively small area such as North Carolina, counties have very different geographic makeups in terms of urbanicity or rurality, socioeconomic status, and these sort of things, which could certainly impact associations. And so we wanted to be able to allow that to vary and to see if we could get some more resolution. And it is in that bottom row that we started to notice differences between the types of heart failure. So you see that the systolic heart failure, which is sort of a more traditional lower ejection fraction heart failure that's been, widely studied across the literature, we see an increase of about 7% in the risk of mortality. Whereas for diastolic heart failure, we see an increased risk of about 12% for mortality. Not a statistically significant difference there, but certainly a trend that makes us think that we should investigate whether or not there are heart failure subtype specific differences that may be due to either the clinical presentation of the disease, medication status, or long-term disease management. Next slide, please. So in conclusion for this, the takeaways of my portion of the talk are that electronic health records really do give us an unprecedented insight into environmental health risks faced by vulnerable populations, this being the currently the largest study of PM2.5 and mortality among the heart failure population to date. Heart failure patients seem to have substantial environmental health risks, which can be seen even in areas that are have exposures below current PM2.5 national ambient air quality standards, and are much more elevated relative to the general population that we've seen over decades of research. And many more studies are needed on specific patient groups with unique environmental health risks, who may be drivers of the overall community health risks that we see when we analyze things in the general population based sense. And finally, we are most certainly expanding these analyses, and we've expanded our EPA Cares electronic health record resource to incorporate people with a previous heart attack, as well as individuals with type 2 diabetes and others, to study a variety of patient groups and really being able to start to understand their personalized environmental health risks. Next slide, please. And with this, I would like to conclude my presentation and with a brief acknowledgement of the many, many groups and individuals who contributed to this analysis, including our especially our collaborators at the University of North Carolina, without whom none of this would have been possible, as well as collaborators at Harvard, who provided some quite essential air quality modeling for us.